So for the second part of this review video, we're going to be solving this problem right here. So for this problem, we're looking at a dielectric with a non-constant dielectric constant. I guess it's more of a dielectric function. However, we have kappa as a function of x equals the square root of x plus 1 over x. And it's inserted into a parallel plate capacitor with area A and separation d. So we have to find two things. One, the new capacitance in terms of A, D, and appropriate physical constants. And two, the potential energy of the capacitor in terms of area, distance, appropriate constants, and delta V. So if you want to try this for yourself, go ahead and do that now, but I'm going to work through it on this board. So we're going to start with this first question, solving for the capacitance. So our original function for capacitance doesn't really work here. We have kappa epsilon naught A over D, and that doesn't really make sense. Your capacitance is a number that represents how much a change in voltage affects the charge on your capacitor, and so it wouldn't make sense for it to be a function of x. However, there is another function that involves our dielectric function that makes a little bit more sense. We know that the dielectric constant also serves to scale down the electric field by some amount kappa. So knowing that, it makes a little bit more sense to use this function right here, plug in our kappa as a function of x into there. So we're going to go ahead and replace sigma with q and a because area is one of the things we want to have in our final result. So we know the electric field, and this is going to be a non-constant electric field between the two capacitors because our dielectric constant is changing. And it's going to be equal to Q over, so it's going to be divided by this function, but the x is going to come up to the top. So x over the square root of x squared plus 1 times epsilon naught times a. So this is our function for the electric field. So we're just going to look through the exact same process as we did when we were originally deriving these equations for capacitors. And so the next step is to integrate the electric field to find the voltage. So we know that the change in voltage is the negative integral of the electric field dx. Now we're going to integrate electric field's a vector, so it could be positive or negative. We're going to integrate against it just so that the negatives go away, because two negatives make a positive, just so that we end up with a positive result for change in voltage. So we're going to substitute that in, and our bounds are from 0 to d, where this is just across the capacitor. So we're integrating qx over the square root of x squared plus 1 epsilon naught a. So the first thing we should do is not forget dx, but we should bring out all of the terms that are just constants. So that's going to be q, epsilon naught, and a, because that just makes our life a little bit easier, makes it a little bit easier to read. Maybe then something will become clear. So, looking at this integral that we have resulting, it's not a standard integral that we can just integrate like off the top of our heads for sure. But it should become clear after a moment that it's pretty easy to solve this with u substitution. If we let u equal x squared plus 1, then du just equals 2x dx. And we can make this substitution because we have an x up here, and we can get the 2 in just by multiplying by 1/2. So we're going to do that. And because we need a 2 inside, we'll have a 1/2 outside. So we have q over 2 epsilon naught a times the integral, and we'll change our bounds of integration just so that we don't have to resubstitute for x. So if we plug in 0 into u, we get 1. And if we plug in d, we get d squared plus 1. And we get the integral of 1 over the square root of u du. So it should be pretty, this on the other hand is a pretty trivial integral that we can solve just by using the power rule for integration. So we'll get, after evaluating that, the change in voltage equals q over 2 epsilon naught A times, and the antiderivative of 1 over the square root of u is just 2 times the square root of u, analyzed from 1 to d squared plus 1. So I'm just going to erase some of the top here just to get this, just to give us a little bit more space to work. And we can see from this bottom result that first of all the 2's are going to cancel out, and then we just have to substitute our bounds. So we get q over epsilon naught A times, so the square root of d squared plus 1, that's just, that can't be simplified, minus, and the square root of 1 is just 1, so we're just going to subtract 1. Now, we're almost done. All that's remaining to do is take this function and solve for q. And then the remaining proportionality constant that we have in front of v is going to be our capacitance. So, if we multiply over EA over d squared plus 1 minus 1, we get q equals epsilon naught A all over the square root of d squared plus 1 minus 1 times the change in voltage. And that leaves us just with this term right here up front being our capacitance, and you can see that everything in here is a non-variable value, and so our capacitance is just going to be a number for whatever capacitor we have. So capacitance equals epsilon naught A over the square root of d squared plus 1 minus 1. So the final thing we have to solve for is the potential energy of the capacitor when charged to some voltage delta V. So what's important to note here is that this capacitance right here is still just a number. Even though we started with this weird non-constant kappa function for our dielectric, the capacitance we ended up with is still just in terms of, I mean, the original capacitance would be epsilon naught A over D for just a standard capacitor, and this just has some more functions in the denominator, but it still just evaluates to a number. So that means that all of our process for finding the potential energy of the capacitor is going to work out exactly the same. So we're pretty much done here. We know that the energy of a capacitor is 1/2 QV, which equals Q equals C times V, so that's just 1/2 CV squared. So if we make that substitution using the second one right here, we're left with just the potential energy equals 1/2 times the capacitance times the voltage squared. And that's it.